starting.
Welcome to the Pittsburgh Functional Programming Meetup.
Yes, apparently.
July 13th.
So, I originally gave this talk to the Pittsburgh Functional Programming Meetup. I'm giving it again, and with a chance to record, to the Personal Robotics Lab at Carnegie Mellon University, inflicting myself upon them. So today, we're talking about performance and functional programming with Rust. So we're talking about the mechanisms that underlie the abstractions we use when we use more functional techniques or more high-level or expressive techniques with programming. This usually involves some set of performance trade-offs to get expressiveness, and we're going to use the language known as Rust to do this. So Rust is a sort of low-level language, but it's expressive, and we're going to use it to explore these concepts. So this won't be a deep dive into Rust, but we'll get introduced to the language a little bit as we go. And do feel free to stop at any time with questions. So a little bit about me, which I'll do for the camera. So I program robots in my day job. This is Herb. We try to get robots working in human environments. But don't worry too much about robots going to take your job, because they still have a lot of trouble. So things we think of as simple, like picking up a bowl or putting down a plate, are actually very complex tasks when you put hardware and software in the real world. So our work, our development is actually a little bit unique in that we both write very mathematical, very expressive code and algorithms in order to enable robots to work in the real world, but we also have to put it on real hardware. We have to, and we also need performance. We publish research based on incremental improvements to the performance over state-of-the-art algorithms, so we need to squeeze every bit of performance we can out of the work that we do. So that puts us into a sort of unique position where basically all we're left with, in order to get some measure of expressiveness, but also the performance, and if we're careful, like real-time and safety guarantees, is C++.
What do you mean by expressiveness?
So expressiveness is generally the idea of, well, we'll talk about it here in a second, that you can write some higher level idiom or some higher level expression, like a list comprehension in Python. So for, like expressing a set, x for, x in where x is an integer and it is greater than 5. Like it expresses some infinite set. It's just an expression. It doesn't tell you anything about how the computer underneath might be handling this data or the creation or generation of the set. And we'll talk more about what it means. So we're going to talk about performance, but before we do that, we want to go into so what does the study of computer science really entail? So from the structure and interpretation of computer programs, this is where the programming language Scheme was sort of introduced. It was used as the introductory CS class at Harvard for a number of years. This was the introductory text. So mathematics provides a framework for dealing precisely with notions of what is. And computation, or computer science, provides a framework for dealing precisely with notions of how to. So computer science, in the end, is the study of computation, process, or of methodology. So we're going to look at through that lens. And then sort of this dichotomy between what is and how to that underlies all the trade-offs we're going to talk about. So everyone knows Alan Turing. We talk about Turing machines and Turing completeness. So Alan Turing described a machine that could emulate a machine that could process symbols given a finite set of instructions. So what the symbols are or what they mean is not important. This is a focus on a process, a way of computation. We implement these symbols, or we implement these machines today on architecture, something known as the von Neumann architecture. So this is a processing unit, a CPU, and a memory unit, we know as RAM. And the memory data is loaded in and out of the CPU from the memory unit, and the CPU can interact with the world via some input and output devices. Again, this is a how architecture. the meaning of the bits flowing through this are not important to the structure itself. This is a way to do computations. Since I was talking with the functional programming group, and I'll explain a little bit, so functional programming sort of motto is don't write down how to do something, write down what you want. Write down some expression, some code that represents what you want out of the end, not the implementation details of how a computer system is going to process that request. And again, that sort of paradox underlies the talk. Okay, so let's talk about performance. So C and C++ are generally known as the most performant programming languages, but in order to examine why that might be the case, we have to talk about what performance is. So you might talk about short response time, so being able to do something just very quickly, time-wise. High throughput, being able to process a large amount of data. You might talk about low utilization of computer resources, so low memory footprint, or low power consumption, especially important on mobile devices. You could talk about high availability, so something that's up 24/7 without ever crashing, something like a rover that you send millions and billions of miles away. You could talk about speed of algorithms, bandwidth utilization, or like transmission times. So there are many metrics you might use to talk about performance, and we generally think of these as lying on some continuum. We usually think of it as this. And so you might have better performance or worse performance. There may be some hard upper bound of as good as you can possibly be, and then you could be infinitely bad. But really, the only point that matters on this is the good enough point. At some point, you will be unacceptably slow or memory hungry or something. At some point, you'll be good enough, or you'll be adding value as you improve performance. And then at some point, you're not adding value to the goal you're trying to achieve. You're just playing a game of trying to optimize. So take everything we're going to talk about with a grain of salt, is that all the languages we'll mention are generally fast enough for most applications, written in an idiomatic way with some sane architecture. But so we're going to go into some when you need to add value, when you hit some bottleneck after you've done extensive profiling, what can you do? How do these things work? So there's one more aspect of performance that's especially important for us and for other high-performing systems, and that is consistency. So a low standard deviation in the performance of the system, and strong guarantees on maximum worst-case situations. So a lot of times this is much more important than the actual value of the metric, is just to say, can I talk about the bounds of my system? Whether you're Google serving content, or you're say a hardware system that runs in the real world like Herb. So as an example, Herb's arms require a heartbeat signal every 14 milliseconds. If they don't get a signal from the controller in that time, they will shut down. The safety system kills them. Why some breaks? It's because if you don't keep constant signal, constant contact, things can go wildly out of control. So it shuts down the safety system. Think about something like a car. Has needs very strong guarantees about everything operating correctly. So we have to be very careful to do our entire control structure, all of our calculations, and then sending messages over a serial line, and then receiving the responses and doing it all again with very precise timing. We can't afford to really to mess this up and have some hardware crash, especially if we want to operate around people. So why are C and C++ considered high performing? Generally, we can break languages down, and the way we're talking this talk are between languages that more specify how something is developed. So on the far end here you have like assembler, or C, or C++. C only abstracts a very little bit above the hardware you're running on. So if you knew the perfect algorithm to implement your system the fastest way on some architecture, you could pretty much implement it directly in C, or directly in assembler if you needed to. And it would be the most performant way to implement that algorithm. However, there's nothing magical about C or C++. You can still do something like this. Does anyone know this algorithm? Yeah, this is Bogosort. It's you want to sort an array, so you check if it's sorted. If it's not, you randomly shuffle the items and check again, and you just continue. And it's just about the worst algorithm that makes forward progress on the sort. So this is C. The memory access is all very efficient and very tight, but you can still write arbitrarily terrible and slow code in a low-level language. In fact, especially the way we do things in this lab, we bet that most people can write more performant Python than C, given the first few tries, if only because a failure is infinitely poor performing, right? If your program crashes or does not compile or doesn't work, you have bad performance by definition. And Python's much easier to write than a correct C program. So on the other side of this list, we have languages that believe either performance is not as important, or that it's not worth the overhead or the danger of having the developer keep all of this stuff in mind and do everything correctly, or that the compiler can do a better job at optimizing common expressions than the developer can. And in the end, both of these sides are correct. So the architectures we actually operate on are far more complex than the model that's exposed. Between pipelining, a large cache hierarchy, branch prediction, simultaneous multi-threading, no developers really understand the way their bits flow through the hardware. And compiler and assembler authors can spend a lot of time optimizing and experimenting to get code to run fast that we might necessarily have time to do. These are all of the optimization passes from the LLVM compiler assembler. So when you compile C with Clang, or compile Swift code, or compile Rust code, and you give it the optimize flag, it does all of these things to improve the performance of your code. However, the compiler is still limited in that it can almost never change the meaning of your code. It can't change the result of what you've asked for. So it's still on us to write code that is both correct and can take advantage of the language, but also hopefully that your compiler can produce efficient machine code with. So what about Rust? We said we were going to use Rust in this talk. So I put Rust just about here on the list. Like C, it is. I like it because you can see fairly straightforward what is going to come out of the compiler, what it's going to look like, sort of on memory, what the flow will look like. It's predictable compilation. But unlike C, the compiler gives you a ton of help writing both efficient, high-level expressions, and that can be very expressive and safe. So from the home page, Rust is a systems programming language that runs fast, prevents seg faults, and guarantees thread safety. Zero-cost abstractions we'll talk about. Things like trait-based generics, pattern matching, type inference are all things you generally see in much higher level languages, something like Haskell or maybe a Lisp. But they exist here in Rust, a compiled language. So let's look at a little bit of code as an introduction. So in Rust, it's not a pure OO language like Java. You have free functions. Main is your entry point. Let program. This is a constant, immutable variable definition. If you want to make it mutable, you add let mute. You have to be explicit. For loops are more like Python than C. For token in all the characters of a string. Match on the token. This match must be exhaustive. If you do not specify this, everything else, it's a compile time error. It won't let you proceed. And this works for all types, anytime you're matching against types or enums. And you can print. So it's not a pure language like Haskell that makes you wrap up I/O or sort of impure side effects in a special structure. You can print what you want. But we're talking about functional programming. So Rust is multi-paradigm. You can write this in a more functional way. So let program, let value, you can do a fold, or reduce, or accumulate, however you learned it, over a closure. And this matches an expression. It returns a value. You don't have to mutate state inside of it. You leave off the semicolon, and you have an expression that has a value. And this goes through all the characters, and you get your calculation at the end. This is a very nice, clean way to write this. We could also write this in an object-oriented way. It's not really a great place for it, but such is life. A struct, this is your product type. It's like your class, your object, it's called struct. You implement things, methods, on your expression, and new is not a constructor, it's just a sort of convention if you want to get a default thing of something. Add takes in a reference to yourself, like Python, and you can mutate it, specify, and we create an expression, and we mutate it, and then we get the value. And surprise, surprise, I wrote this for a functional programming meetup. The functional version is much prettier, right? But you can do this sort of thing in Rust, and sometimes it's very nice. One other thing we'll talk about first before we jump into some performance is the trait system. So traits are the interfaces in Rust. They're the type bounds and guarantees. So I can have a trait called random, and it just says anything that implements this trait has a function called random, doesn't mutate itself, and it returns some integer. Oh, as I'm going through this, we haven't seen a type definition yet, but all of this is strictly statically typed. It's just the compiler is smart enough to say, I know you're assigning this an integer, so this is an integer. You don't have to specify it explicitly, though you can if you want. And you must.
Is that second line not specifying type?
This line?
The
So
I-64?
yeah.
The I-64, is that
Yeah,
not specifying?
so functions must specify the type signature. Now, Haskell lets you skip it, because it can infer it from definition. Rust just says, no, for functions you must specify the type exactly. For lets and other things you don't. So we can create a unit struct. This is just an empty object that we'll just use to implement this trait. The XKCD algorithm for random number generation. And we'll have a function that has a type bound. So this says, I take a type T that must implement random. And then I'll print out 5 of them. And that works. So again, these traits are runtime or compile time checked. And you can either write new traits yourself and implement them, or you can implement traits provided by the standard library, like a trait called add, which lets you override the plus operator, like you might do in C++. So all these languages are abstractions, and abstractions give us power. You can wrap a lot of complexity behind a simple, comprehensible idiom. And so we move from something like machine language, x86, assembly, hello world to Python. Sometimes what we're doing is inherently complex, and we can't avoid it. We just have to try to deal with it. But sometimes it's these the abstractions themselves to blame when we run into poor performance. So the author, the creator of the C++ language, coined this term zero overhead principle. So the underscore script. What you don't use in a language, you don't pay for. So just because some feature exists, if you don't use it, you shouldn't suffer for it. And if you do use some abstraction, you couldn't hand code any better. You couldn't find a better way to to write the code than what the compiler produces, by guarantee. So we're going to look at some abstractions and see sort of the cost of the mechanism underlying. So the first one is memory. So we all know the computer has dynamic memory and RAM, and it's generally split up by our operating system or by our runtime into stack and heap. So something like in Java, if you have a local variable, it goes on the stack. If you say new something, it goes on the heap. Python, Haskell, and other higher level languages just automatically put pretty much everything on the heap. They abstract this away, you have no idea where your data is, you're not supposed to worry about it. C++, when you use the new operator, it gets put on the heap, but it returns a different type than, unlike Java, which is unified types, everything is the same type, you don't know. C++ and C return a different type. So heap's useful for when you either have very large data, because the stack can be a relatively small portion of memory, or if you need something to outlive a function. If you need to return something from a function, or create something and have it persist, you probably need to put this data on heap. So if this is talking about lifetime in space, why is this a performance question? So this heap is literally a heap, as in a bunch of crap just piled together. So there's no consistent ordering. Whenever you allocate memory, it's a search. You're searching through memory for a contiguous space large enough for what you've asked for. So not only can this be very slow if you have to search a long ways through your 8 gigs of memory, it's also non-deterministic. So it depends what the results, if you get a successful allocation, and how long it takes depends on the state of everything else running on your system. You can't say for certainty what's going to happen ahead of time. In C, this is made very obvious. You have some pointer, which is just says I'm pointing to memory, and you call a function that you give a size, and it asks the operating system for some space. And then you cast that to the thing you want. It can fail, you have to check, and it doesn't even clean up for you. It's just a bunch of crap. You have to zero it out yourself if you want to, some guarantee. So C is trading ease of use for a lot of power, because we can actually replace this call with a custom one. Game developers generally always do this. They'll write some custom allocator that grabs a big chunk of memory at the beginning and then handles it. They handle allocations themselves because they have a lot of knowledge about how their program's going to work. They can do this very efficiently. Or you can be like NASA and just never allow this, ever. And you must do everything on the stack. Because this is non-deterministic, you don't want to have failure to allocate memory on your rover on Mars and then crash. Not going to do anything. So you can just avoid this altogether. So Rust actually takes this a little bit from after C here, in that you must explicitly say you want something on the heap, and that's done with the box type here. So if I have a point data structure that has a couple things, I can either declare a point, and then it's on the stack, guaranteed, or I can say I want a box of a point, and a box says I will allocate that thing on the heap. And again, you get a special type. If you have a box, you know you have some heap allocated data structure. And this code, if you run it, just shows that, yes, if I have a point itself, I have 2 ints worth of data on the stack. If I have a box of a point, I just have 1 pointer's worth of data. So there's a more insidious problem here, though, than just the cost of the allocation. What happens when you are done with some memory? How do you let it go? So if we say we're lazy, it's not a big deal, it's a short program, we could just not clean up after ourselves and let the operating system take care of it when we're done. Old computers, that wouldn't work. You'd actually never reclaim that memory until you rebooted the computer. So you have a lot of crappy programs, and all of a sudden you don't have any RAM, you have to reboot to make your system work again. So in C, you call free. You must give it a pointer that you got from malloc. If you give it a different pointer, segfault. If you use that pointer after you freed it, segfault. If you're unlucky, you use a pointer after you freed it and you corrupt your own data. If you free it twice, segfault. So this is not so good. It's very difficult to get this right. It's the source of just an overwhelming number of bugs. So high-level languages deal with this with garbage collection. Garbage collection was actually invented for Lisp by John McCarthy back in the 50s as a way to abstract all this away. So generally what happens is a garbage collector traces the graph of references in your program. It goes through the memory and says what's pointing where and follows all the way down, and it flags things that are not pointed at anymore and flags them for garbage collection. They can be reclaimed. This is a lot of bookkeeping. And there's actually been some studies that show basically garbage collected programs need about 5 times more memory than a manually managed program before otherwise their performance starts to degrade a lot. You can also end up with things like reference counting, but in the end you often end up with a stop the world phase where, okay, I have all these things flagged, now I have to clean them up. I cannot allow my program to keep executing while this is cleaning up because some reference might change, memory might move around underneath you. So you actually have to stop execution, clean up a bunch of stuff, and then continue. Stop the world collection. In Java programs, this can end up like seconds where you don't run while it's cleaning up. And Java, like high-performance systems, spend a lot of time tuning the garbage collector parameters to avoid these sorts of things. So C++ actually has a nice idiom for dealing with this without a garbage collector. It's just got a horrible name. So it's called resource allocation is initialization, RAII. And all it means is instead of saying new and free everywhere and probably messing it up, I put a new inside the constructor of some wrapper. I allocate my data here when I need it. And then in a destructor, I delete it. Why this works is C++ guarantees deterministic calling of destructors. So garbage collected languages don't, for whatever choice they made, deterministically call your destructor. It may or may not get called, and it may be called at different times in different situations. C++ guarantees that when your object goes out of scope in the language, the destructor is called. So this automatically cleans up after itself at the right time, deterministically. And modern C++ even provides some wrappers like unique and shared pointers to wrap all this up for you if you don't want to write this silly wrapper class. You don't need it. So this is why C++ developers aren't clamoring for garbage collector. We actually have a very nice idiom for dealing with it. And this actually works very nicely for other things like file handles or network connections, sockets, things like that. The same idiom works just as well. So Rust follows this pattern. Any program or any type can implement the drop trait, which you specify a drop function method that is called deterministically whenever your object goes out of scope. And box implements this trait. So whenever you allocate some memory to the heap, box has the memory allocated automatically, and then as soon as the box goes out of scope, the memory is deallocated deterministically. So there's no runtime overhead. When you compile, deterministically you know where you need to free the memory, and the machine instructions are generated right there. So there's no runtime overhead. Okay, so that's the first abstraction. So I said the P word back there, pointer. And so now the second thing we want to abstraction we want to look at are values versus references. Okay? So values are the things we care about. You know, the character C, the number 5, the string hello world. But we often end up under the covers with a reference. So here in this, like, say, 8-bit system, I might have a value 5. And that's fine. That's all I care about. It's on the stack. But then here, I want a long, but I have a reference to it. I can't fit the whole data for whatever reason. So I have an address. All a pointer is a parameterized type, which is parameterized on the type it points to. Its value is an address. So I go down to this address, and then I have the value I cared about originally. Okay? So references is sort of an abstract concept. Pointers are sort of one concrete implementation of something that points at something else. Confusingly, C++ and Rust have both pointers and references as part of the language. In C++, you'll deal with it all the time. In Rust, you never deal with a pointer unless you're doing something like calling a C library, doing some unsafe thing. So different other languages generally abstract this away. In Python, you just pass the name of the thing. Same with JavaScript. And Haskell as well. Or even Java, you just pass a thing. And whether or not it's a reference or not is taken care of by the language underneath. But these subroutines are very fundamental to computer science, parameterized, reusable code, and how we get the data into them is very important. What happens under the hood is as we add functions, we call functions, we're copying our arguments, pushing them onto a stack by value, by whatever the value of the thing is. So here I call foo, I save some register, I push an argument, and another, and some return address. And then from foo, I call bar, and then I push another set of arguments and local variables on the stack. So whenever you're evaluating performance, anytime you hear the word copy, you should cringe a little bit. So if I'm passing 3 ints in by value, it's like 192 bits generally. So not a big deal. If I'm passing 3 1 kilobyte structs, I'm copying 3 kilobytes whenever I call that function. If I pass 3 pointers to 3 1 kilobyte structs, I'm again probably passing 192 bits. So the way we get memory into these functions is very important for performance.
So whenever you're passing a pointer, the actual reference object lives on the heap?
Yep. Mm-hmm. Yep. Mm-hmm. And that's how you can get things like use after free. You free it over here. This has a pointer. It's pointing to the heap, but it's gone. Yep. That's what's happening. So Rust makes you do this explicitly. You have to say, if I give an ampersand, I have a reference to a thing. If I don't, it's a value. But why do I care? So why force me to do this? These other languages sort of manage it by themselves. But the sort of Python, Java group, and the Haskell group both make different trade-offs by providing the same abstraction. So in Haskell, or Clojure, you're encouraged to treat everything like a value. Encouraged. But if you have some large data, we already know that this is very inefficient. So what happens? So under the hood, in order to guarantee if you take in some data, and you alter it and return changed data, you actually implement this persistent data structure under the hood. So you only copy or change what is absolutely necessary, and the original structure remains intact. So the original caller has its data unchanged. It's completely immutable. So these are very nice. These are very powerful. They're generally pretty performant, and they're even thread safe. However, they require garbage collection in order to clean up these dead branches without very nasty side effects that can result in like stack overflows and the rest. So Clojure and Haskell will do something like this. And they make so that's one trade-off. Something like Python, you just have a mutable reference. It's a reference, and whoever you gave your data to has your data, and everyone and their mother can alter it. So you end up with crap like this. You give some data, and you have no idea what's going to happen to it. Again, it's very efficient. You're only copying a pointer. However, there are a lot of dangerous cases and a lot of bugs pop up. Mutable state is called the default. So Rust gives you options, and those options are there to give you power. If you wanted to make a purely functional sort of interface with Rust, that's very efficient. You could pass in a reference to some data immutably, and you return a new thing. If you want to change it, you have to pass in a copy. So you take your data, copy it explicitly, change it, and return it, and then your old data and your new data are both fine. Unfortunately, this is not efficient. This actually generates a copy. You generate the data once, and you copy it out.
So is that last line equivalent return your data in C?
Yep. Yeah. Oh, sorry. Yeah. Because Rust is an expression. This whole function is an expression. This last one, its expression is just its own value. So this is a return your data call here. So this is generally optimized away by something called named return value optimization. C++ does this. So if you have a name of something, a named thing, and you return it, and you're just assigning it to something outside of your function, you can just construct this data in place out here, outside, and put the data there once and never copy it. Rust doesn't implement that yet. It's on the list. This is actually not efficient. This is copying. So I learned that while doing this stuff. So we can get around this. We can also do some, okay, so on the flip side of that, so non-named return value optimization, just return value optimization. This is very efficient. So this does the right thing. This thing doesn't have a name. It's constructed here and returned, but it's just constructed in place where you assign it out here. So this does the right thing. This happens efficiently.
Hey, Clint,
Yeah.
what's the analog to like having const in C++ in the signature where you promise that you won't change like?
Yep. So that's the
that
same.
the-
So it's by Rust. That's the default.
Okay.
Rust is the default. In C++, if you specify const,
Right.
you generally can't alter that thing. There actually is an escape hook. You can like just cast it to non-const,
Yeah.
but that's
But you-
crazy talk. Yeah. But yeah, const is the default
I
in
see.
Rust, and the default in C++ is mute.
Right.
Okay.
Sorry.
Yep, that's what happens. Right. So if you wanted to get around that little performance bug, you can take a mutable reference to a thing and return a reference, and you get this sort of pattern. This is a very common pattern where I have a thing, and I just keep transforming it and reassigning to it, just shadowing that variable over and over and over again. It's a very common pattern in functional programming. It's still a little bit mutable.
The functional this
Yep.
thing.
Yeah, sorry. Yeah. So it's mutable inside, returns like another.
You still want to have function data as opposed to input in the output.
Right. Yeah. So this isn't so great, and anticipating pissing off the room at the functional programming meetup, I argued here for a more procedural implementation. So if you get over your distaste for mutability, you can actually write an API like this, which ends up a very, very nice functional API for a library or function. You just happen to be mutating on the inside here safely. So, but why this might not be such a bad idea in Rust, let's look at why do functional languages really care about mutability? So why avoid mutation? There are generally two reasons. So the first is safety. or specifically safety with concurrency. If you pass your data to some other thread or to some other function, you don't know who's mutating it when. There are no guarantees. So if you have immutable data, synchronization is trivial. You don't have to synchronize because everything's immutable. Only copies or reads are allowed. But Rust actually deals with this problem with a different mechanism. So Rust implements in the compiler what's known as the borrow checker. So if I have some data, I own that data. It's mine. I created it. If I give it to someone else, like here, this thread is trying to use this data, this is a compile time error. Because this thread might last longer than the thread that responded, than this thread where the data was created. So this data might be cleaned up and gone when this finally runs. This is a database. This is a compile time error in Rust. The same way, if I explicitly say, okay, move, I'm giving you my data. It's yours now. And then this works just fine. The data lives inside this other thread. But if I try to use it back outside in my first thread again, error, compile time error. I don't own it anymore. I gave it away. So these types of things are prevented at compile time in Rust.
So is it like unit pointers?
Mm-hmm.
Is it like unit pointers?
Something like that. Yeah. Yeah. It's like a slightly stronger version of the unit pointer. There's actually a lot more that happens here, but the unit pointer is one part of this. You can also, so you can extend this further with, this happens for general function calls, whether you give something a reference. It's a compile time read-write block. You can have many readers, only one writer, but cross threads, you're not allowed to do something that's safe.
So the move is a reserved keyword that takes all of the data. So first of all, you're defining this thread as just what it was in those braces.
Oh yeah, this is a closure. So this is like an anonymous function. And this is any arguments code here. And move says anything I've accessed here,
Or in the arguments.
yeah, inside this closure, take ownership of it. Explicitly give ownership. You can also do things like, so if you take an argument, so you're using like a closure in a loop or something, you explicitly can say, hey, I'm taking an argument by reference, just like a function, or you can say, I need to own this, so you must move that argument into me. Or you can copy by value, it all depends on the type. If you use a
So
closure.
he has options to move, or what if you have some stuff you want to?
It only takes whatever you've used. So if you've used it here, and you call move, it takes everything.
And
You can also
move it, it's an error anyway, so you have to move it all.
right. You could
can't move some of it.
right. For thread, it's a little tricky because you can't pass arguments to the start. Other places, other ways you can start this, you can be more explicit inside your parameters about what exactly you want to move, what you want to copy, and you can break it down very finely if you have it.
Could I replace the word move there with copy?
No. But you can implement a trait. If you implement a trait on your data, it will copy by default. So like all primitive types. If I use just an integer here, it would not complain because I'm just copying an integer. So you can make that choice for your type, whether it's something that's more efficient to copy or something you need to be more careful with. And you just implement a trait on top of it. Furthermore, so this whole concept is extended by traits and types in the standard library, so you can have things like shared pointer, reference counted, read-only containers, read-write containers. You can do things that only make a copy if you're going to write to an object. You maybe want to mutate something. So you can take a reference that does no copying. You don't, but as soon as you write, it generates code for copying the object to be more efficient. So this includes things like mutexes that are very ergonomic, very easy to use in background object code in the type system. So the second reason people usually talk about immutability being good is it's more like mathematics. So if I say x equals something in an equation, the x doesn't change. It just means it stands for something. However, just because you know what things mean in an equation does not make that equation clear if you don't already know what you're looking at. Just the fact that t and v are well defined and constant does not make this expression clear if you don't already know what it's doing or what the code is. So the same way, when we develop code, we have to choose the right abstractions. We have to write good, clear code in order to get these sorts of benefits. Immutability doesn't provide them by default. It can only help make things clearer in some cases where it's appropriate. So Rust makes everything immutable by default. You can use mutable structures where it's appropriate. You choose your abstractions and the costs you're willing to pay. So one more abstraction is the abstraction of strictness or laziness. This is definitely more relevant to the functional programming people. Haskell is a non-strict language. What non-strictness means is when you reduce an equation, unlike grade school where you say, okay, please excuse my dear Aunt Sally, inside the parentheses, add these together, and then add them outside, you actually reduce from the outside in. So you say, I have a thing, I'm plus with another thing, and then I go in and evaluate this thing if necessary. What this lets you do is you can actually have error-valued terms in an expression, depending on some state, and if they're not evaluated, if you don't reach them, your whole expression does not reach bottom. Your whole expression is not necessarily error-valued. So it allows you to express things that are impossible to express in strict languages. So there are only a couple languages that implement this. Haskell is the only modern one, Clean, and there are a couple others. But the way it's implemented is with something called laziness, which is something quite different. Most people are generally concerned about laziness. So before we do, so strictness, an example of some weak form of non-strict evaluation is like the shortcutted or. If I have a null pointer here, dereferencing it is error, right? Segfault. But if I have true, if true, or, I never evaluate this, right? I'm evaluating one side. This just doesn't matter. This always executes, and there's no error. This never executes. I never get an error term. So this is sort of an idea of what non-strictness can buy you. Like you can do lots of tricks with just this. There's more you can do with a fully non-strict language. So, but you have to implement it somehow. And what that's done is it's implemented with laziness. So what laziness means is I have some expression, and when I use these expressions, I don't actually evaluate their value just on assignment. I wait until I actually need their value to do the evaluation. So I just sort of store expressions all the way down the pipe. These are known as funcs. They're generally stored as like little anonymous functions by the compiler. So I just keep sticking things in, and then if I print result, I need to evaluate this in order to get that value, or if I want to test it against some condition.
So you're saying from a programmer's perspective, if I were to write those 4 lines like one gigantic expression versus this, there would be no performance difference.
Yep, it would just do the same thing.
Except maybe the space of the program.
Yep. Yeah, and afterwards it might end up even just doing the same thing.
Okay.
Yeah. So this can be both very beneficial and also very harmful to performance. It's very good if you have some very large expression that you end up not needing, you don't evaluate it. You just don't pay the cost at all. You never evaluate it. However, it's not necessarily easier to store this expression in memory than just evaluate it immediately. Haskell actually gives you, there are several techniques you use to say, evaluate this strictly. Like just evaluate it right now. I know it's more efficient that way. Or you have to be very, very careful when you write functions to make sure you've written them in a way that it evaluates them in a strict, non-lazy fashion. Otherwise, you can end up with extremely poor performance. And more importantly, for us, non-deterministic performance again. You don't know when your code's going to be run. It's very hard to analyze unless you're very intimate with the Haskell language and compilers and the semantics of non-strictness and lazy implementation. So one other nice thing this buys you, though, is being able to work on like infinite sets. So if I can just define an infinite set of integers and do operations on it, and it's going to perform efficiently because I'm only going to use as much as I needed in the end. But all of this laziness is actually just the same abstraction as iterators. In Rust, I can say I have a range from 1 to 1,000,000, and I can map over it, doubling every item, take 5 of those items, and then collect it into a vector. Map is only called 5 times, guaranteed. And VS is only 5 items long, even though I have a range of 1,000,000 or 1,000,000,000, however many I want to put in there. I could have an infinite stream of things I'm mapping over, or I'm chaining, or zipping, or filtering. And they're only evaluated when I call something that needs to finish the evaluation. When I collect them into a collection, or when I call any to check some condition, like a true-false predicate. And this is exactly as efficient as a for loop, just doing the for loop over X items. So there's zero cost, it's lazy sort of by design, and it gives you the same, provides you the same abstraction.
Is V stored as a Boolean length vector?
It is not. V is stored as a range object. It's something that represents some large set. Yep. And it's only evaluated down here. So one thing I wanted to mention, I'll just do it quickly, a little bit out of time. So everyone's favorite library, Eigen, in C++. Eigen is efficient, actually, because it does a form of thunking, of laziness. But it actually does it at compile time. So C++ generic programming is done through templates, which is a form of metaprogramming, code that generates code. But the template system in C++ is actually Turing complete. You can evaluate expressions with it. So the way Eigen is implemented is something called expression templates. When you say matrix transpose times something, that is a giant AST, like a syntax tree. It's a giant tree of expressions in templates. And when you compile, those templates evaluate down, recognize patterns, and optimize your expression up until the point where you assign it to something and need to evaluate the final matrix or vector. So it's actually doing thunking, like storing expressions and not evaluating them at compile time to do optimizations on like a big tree. That's how Eigen is very efficient. It can be more efficient than even like hyper-optimized Fortran libraries that can still only work on one operation at a time. Rust does not have the equivalent to Eigen yet. It's probably the biggest thing holding it back in our domain. But it has a macro system that's not copy and paste like C that can actually, and you can even do compile time macros that would be able to do the same thing, have code that generates code.
Question, and I may be wrong here, but does Eigen have like sparse matrix support, like separate data type?
It
And
does.
I'm wondering if, wouldn't that require some compile time stuff, like, because you're storing it in a different way than you would store like a dense matrix.
Yep.
But does this only refer to like evaluation of function?
So that's the evaluation. There are like, you can import like eigendents. There's also like other parts. And there are also, like you can also memory align. You can use eigen in a way that memory aligns it depending on your architecture so that you have better cache optimization and stuff. And then you have to be very careful, like you can only use its very specific methods. If you try to access it like an array, you're gonna get junk in it. Yeah. So there's lots of other details in eigen that make it efficient and stuff that are possible in Rust when doing the memory managed stuff. But the AST, like the expression templates, are not yet. Okay, so we talked about a lot. We didn't cover a lot though too. So we didn't talk about the cache. Keeping a warm cache, like keeping your data close to the CPU is very important. And there are ways you can optimize that. If you pull one data out of a register, it actually costs less than a cycle of CPU time because it's prefetched. If you have pull something from cache, you're maybe talking on the order of 10 CPU cycles to pull the memory. If you pull something from RAM, you're talking hundreds of CPU cycles. So optimizing your data structures and your code to actually keep your cache hot is very important for performance. Polymorphism, dynamic runtime polymorphism, has a cost. In Rust it does not, because polymorphism actually generates static code. In runtime polymorphism, like C with virtual functions, there's a performance dip. And this actually explains Aikido. Aikido avoids this very explicitly. It suffers a lot in the API for it. We didn't really talk about concurrency. So the big value add for languages like Clojure and Rust and Haskell are that you can write concurrent programs very easily. And being able to use concurrency and parallel processing easily, safely, and efficiently really changes the game. It completely changes the way you can think about writing efficient programs. So in the end, there are no wrong choices for these languages. You just have to understand the trade-offs you're making. And hopefully today we learned a little bit about that. You need to profile, find the bottlenecks when performance is important to you, and do the optimizations that you need in the language that you have, using the tools like the compiler that work best for you. So when you consider your options, I do hope you consider Rust. It's a great language. But we'll stop now and see, does anyone have any questions?